Section 4.2, Addition Rule and Multiplication Rule. Remember, a compound event is an event combining two or more simple events. The notation for the addition rule, probability of A or B, means the probability in a single trial event A occurs or event B occurs or they both occur. To find the probability of A or B, add the ways that event A can occur and the number of ways that B can occur, but in such a way that every outcome is counted only once. The probability of A or B is equal to that sum divided by the total number of outcomes in the sample space. Here's the formal addition rule. Probability of A or B equal to probability of A plus probability of B minus the probability of A and B, where probability of A and B denotes the probability that event A and B both occur at the same time as an outcome in a trial of a procedure. Think about creating a Venn diagram for two sets. So this is trying to give you some intuition about where the rule comes from. Notice here that the probability of A is going to be represented by the circle labeled A. Probability of B is represented by the circle labeled B, and the probability of A and B is represented there in the intersection. And you notice that region in the center is actually part of the circle of A and the circle of B, which explains why in the formula we have to subtract off that region because it's being counted twice if we simply added the probability of A plus the probability of B. Disjoint or mutually exclusive events are events that cannot occur at the same time. That means that their disjoint events do not overlap. So, example of disjoint events. Event A, randomly select someone for a clinical trial who was a male. Event B, randomly select someone for a clinical trial who is a female. The selected person cannot be both. Example of events that are not disjoint. Event A, randomly select someone taking a statistics course. Event B, randomly select someone who is a female. We can pick someone who is a female who is taking a statistics course. The addition rule with disjoint events, when events A and B are disjoint, then the probability of A and B is equal to 0. So then the addition rule becomes probability of A or B is equal to the probability of A plus the probability of B. And think about this with a Venn diagram again. This time the two circles in the Venn diagram do not overlap. Probability of A is represented by the circle labeled A. Probability of B is represented by the circle labeled B. And since probability of A and B is equal to 0, the two sets do not overlap, and that's why we don't need to have that last term in our addition rule when we're working with disjoint events. Here's a summary of the key points of the addition rule. To find the probability of A or B, first associate the word or with this addition. To find the value of A or B, add the number of ways A can occur and the number of ways B's can occur, but be careful not to add without double counting. Complementary events and the addition rule. We use A with a small horizontal bar over it to indicate the event A does not occur. That's called the complement of A. Common sense dictates this principle. We are certain with probability of 1 that either event A will occur or it will not occur, so it follows that the probability of A or B must be equal to 1. Because events A and A complement are disjoint, we can use the addition rule to express the principle as follows. The probability of event A or A complement is equal to the probability of A plus the probability of A complement, and that's equal to 1. Which leads to a couple of variations of that. The second one, probability of A complement is equal to 1 minus the probability of A, or the probability of A is equal to 1 minus the probability of A complement. Here's an example. Based on a journal article, the probability of randomly selecting someone who has sleepwalk is 0.929. So the probability of sleepwalking is equal to 0.929. If a person is randomly selected, find the probability of getting someone who has not sleepwalked. Using the rule of complementary events, the probability of selecting someone who has not sleepwalked is 1 minus the probability that they have sleepwalked, or 1 minus 0.292, and that's equal to 0.708. The probability of randomly selecting someone who has not sleepwalked is 0.708. The multiplication rule, probability of A and B, is the probability that event A occurs in the first trial and event B occurs in the second trial. The probability of A with that small vertical bar means the probability of event B, given event A has already occurred, is used frequently in the multiplication rule. This represents the probability of event B occurring after it is assumed that event A has already occurred. To find the probability that event A occurs in one trial and the probability of B in another, multiply the probability of A by the probability of B, but be sure that when we figure out the probability of event B, we assume that event A has already occurred. And that leads to the formal multiplication rule. The probability of A and B is equal to the probability of A times the probability of B given A has occurred. Two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. Since events are independent if the occurrence of any does not affect the probabilities of the occurrence of the others. Several events, rather. If A and B are not independent, then they are said to be dependent. Let's work an example. 50 test results from the subjects who used drugs are shown below. Of the 50 subjects, 45 had a positive result and 5 had a negative test result. If 2 of the 50 subjects are randomly selected with replacement, find the probability the first person selected had a positive test result and the second one selected had a negative test result. And then we're going to repeat part A, but this time we're not going to replace the subjects after we select them. So for part A, with replacement, there's 45 positive results among the 50, so the probability of a positive result is 45 over 50. On the second choice, we're going to put that first person back, so there's still 50 people. Now we want to get the probability of 5 negative test results among the same 50 total results, and that's going to be 5 over 50, since we replaced the first subject. So the probability the first selection is positive and the second is negative with replacement is 45 over 50 times 5 over 50, and if you multiply that out and simplify, you get 0.0900. Now we're going to do part B without replacement. So the first probability will be the same. It will be 45 over 50, but we're not going to replace the first person. So when we go back in the second time, we still have 5 negative results, but we only have 49 people to select from. So the probability of the first result is positive and the second is negative when we're not replacing the first subject is going to be 45 over 50 times 5 over 49. And if you multiply and simplify, you get 0.0918. In the world of statistics, sampling methods are critically important, and the following relationships hold. Sampling with replacement, the selections are independent. Sampling without replacement, the selections are dependent. Use the data in the table, which lists drive-thru order accuracy at popular fast food chains, to answer the following questions. Assume that orders are randomly selected from those in the table. What is the probability of selecting an order from restaurant A? So we notice in the table we don't have any totals. So the first thing we need to do is get the totals. So I put the table down below and I've got the total for each of the restaurants and then also the totals over here. These are called marginal totals for the total number of accurate and inaccurate orders. Now we can answer the question, what is the probability of selecting an order from restaurant A? So A had 370 of the orders out of 1,111 for 0.333. What is the probability of getting an order from restaurant A or an order that is accurate? And now we can use our addition rule. So we'll use the probability of A or B, the probability of restaurant A or accurate, probability of restaurant A, which we just did here, plus the probability of accurate, which will be 971 over 1111, subtract the probability of restaurant A and accurate, which is 335 over 111. And if you go ahead and simplify those, add them and subtract in the numerator and simplify, you get 0.905. Are the events of selecting an order from restaurant A and selecting an accurate order disjoint? No, because we can select an order from restaurant A that is accurate, so therefore they're not disjoint. Now we're going to select 2 orders from restaurant A, and we're going to sample with replacement. So the first order, the probability it's from restaurant A is 370 over 1111 times the same fraction, and we come up with a probability of 0.111. Now, are these independent? These events are independent because the probability hasn't changed given that the first event has already occurred because, again, we're sampling with replacement. Now, what if we do without replacement? So the first choice is going to be 370 over 1,111. We're not going to put that order back. We're also going to assume it came from restaurant A. So the second probability is going to be 369 over 1,110. And if we multiply and simplify, we get 0.108. Are these events independent? No, because you notice on the second probability, it has changed because we sampled without replacement. We didn't put the first order back, and we assumed it came from restaurant A, so the second probability changed. The principle of redundancy is used to increase reliability of many systems. Our eyes have passive redundancy in a sense that if one of them fails, we continue to see. An important finding of modern biology is that genes in an organism can often work in place of each other. Engineers often design redundant components so that the whole system will not fail because of the failure of a single component. And this is used frequently in the aircraft. So they have critical parts here, and one of those critical parts is the independent hydraulic systems, and the Airbus 310 twin engine actually has 3 of those systems. So if any one of those systems fails, full flight control is still maintained with another functioning system. So let's assume the probability of a failure of a hydraulic system is 0.002. So if the Airbus 310 only had one hydraulic system, what's the probability that the flight control would work for a flight? And then given that it actually has 3 independent systems, what's the probability on a typical flight that control still can be maintained with a working hydraulic system? So for a single system, we're going to have one hydraulic system. The probability of that system failing is 0.002. So the probability that it doesn't fail is going to be 1 minus 0.002 or 0.998. Now we're going to make things better. We're going to have 3 systems. So the probability that all 3 fail, because they're independent, is 0.002 times 0.002 times 0.002, and it's a very, very small probability. It follows that the probability of maintaining control, the probability does not happen that all 3 fail, is 1 minus the probability that it does. And if we notice here, we have a very high probability that we will not have a failure when we have redundant systems, much higher probability than we had when we only had one system. So with only one system, we had a 0.002 probability of failure, but with 3 independent systems, very, very small probability. So much better to have the 3 hydraulic systems, and it's increased by a factor, decreased not by a factor of 1/3, but by a factor of 1 over 250,000. So it's a much safer system that way. So summary of the 2 rules. Addition rule, think of addition and the word or. Probability of A or B suggests we add, and multiplication rule and suggests we're going to do multiplication. Among a group of subjects tested with this one-panel THC test for marijuana use, which is provided by the company Drug Test Success, the following results were obtained. Among 143 subjects with positive test results, there were 24 false positive results. Among 157 negative results, there were 3 false negatives. How many subjects are in this study? So the first thing they suggest is to make a table. So I'm going to make my table, and I've got 2 categorical variables, positive test, negative test. Use marijuana, they don't use marijuana. So let's look at the positive results. There were 143, and they told us also there were 157 negative results. So we can put those in the table. Of the 143 positive, there were 24 false positives. So that means that they were positive, but they don't use marijuana. So that goes into this cell here. And then by subtraction, I can find the true positives, which is 119. And then let's work on the negative side. So of the 157, there were 3 false negatives, which means they used marijuana. And then by subtraction, I can find the true negatives, which is 154. And then I can add across each row to get the row totals. So how many subjects were in the table? In the study, rather, 300. How many subjects did not use marijuana? 178. So now what's the probability if we select a random selected subject from the table that they didn't use marijuana? 178 over 300. What's the probability a randomly selected subject tested negative or used marijuana? So tested negative, negatives here, 157 over 300. Used marijuana, 122 over 300. And then we have to subtract the cell right here, 3 over 300. They use marijuana and they test it negative, and we come out with an overall probability of 0.92.